Okay, we are going to work through the free response from the second part of the 6 weeks exam, the non-calculator portion. I hope that this works and you're able to see or hopefully zoom in on the video. I'll also post a hard copy of the answers just so you can see it. So we have this function, consider the rational function f of x equals the given function to answer the following questions. And then it goes through to ask about some limits. So the first one is it asks us to find the limit as x approaches -1 of f of x times 2 times the cosine of pi of x. And it says show your analysis applying the properties of limits. All right. So it's really important that when you work this, you show some sort of limit notation as you're working it. So really what we're basically going to do is we're going to take the limit as x approaches -1 of f of x times the limit as x approaches -1 of 2 times the cosine of pi of x. And then we're just going to do some direct substitution. Now the issue with the limit of f of x as x approaches -1 is that we end up with 0 over 0. So we need to be able to actually simplify this. So if you come over to the side and simplify it, that's fine. Or we can continue right here just to rewrite this in factored form. So I'm going to do, this is going to be 2x plus 1, and I believe it's x plus 3. There we go. And the denominator factors into x minus 4 and x plus 3. And that allows us to cancel our x plus 3's. Those factor out or divide to give us 1. So now we can do our direct substitution. All right. This is still times the limit as x approaches -1 of 2 times the cosine of pi of x. Now I'm going to do my direct substitution, and once, well, let me scoot that over. Once I do my direct substitution, then I can drop the limit notation. So now I can actually evaluate the limit by plugging a -1 into the equation. So I'm going to come out here and do it on the side. So I'm going to have 2 times -1 plus 1 over -1 minus 4 times 2 times the cosine of pi times -1. And now we're just doing math. So this is going to be -2 plus 1 is -1 over -5 times 2, and the cosine of -pi is also -1. So I end up with 1/5 times -2, which is -2/5. And you just work it down and work it out. So where we use the property of limits is right here, in that we can the limit of the product of two functions is the same as the product of the two limits. So just showing that, breaking that down, and using your limit notation. All right, part B. Does f of x have any vertical asymptotes? And so at this point, I'm going to ask you to go back and look at your notes and see in your notes where it talked about what we have to use to justify the existence of a vertical asymptote. And what we have to use is the limit notation. We have to say that if the limit as x approaches a of f of x from the right or left equals positive or negative infinity, then we can say that x equals a is a vertical asymptote. But not until we do that can we say it's a vertical asymptote. So when we look at f of x, we see that the limit, well, let's actually come over here. We see that f of x, let me think how I want to do this. Well, what we end up having is we saw that the limit as x approaches -1 up here. Let's just look up here. Sorry, I'm kind of thinking through this as I go, which is good for you to see my thought process. So up here we see that we can simplify f of x. Okay, so we can say that f of x is equivalent to 2x plus 1 over x minus 4 as long as x does not equal -3, because these factors aren't actually gone. They're just saying that this is equivalent to f of x as long as everywhere except at x equals -3, because if at x equals -3 we actually have a hole. Okay, so here's what we can say. So we recognize that this function right here, Okay, f of x has a removable discontinuity at 3, but it's going to have a non-removable discontinuity at 4, so it's going to have a vertical asymptote at 4. So what we look at is we go, okay, we're going to check out 4, and we're going to see what's happening to f of x as we approach 4 from the left, okay? And we know it's approaching positive or negative infinity because if we plug a 4 in, we get 9 over 0, okay? Which means we definitely have a vertical asymptote there. It didn't remove out, so 4 is going to be a vertical asymptote. We just have to prove why. So we know it's approaching positive or negative infinity as we come at 4 from the left. And we just have to show our algebraic or our justification for that. So we're going to pick an x value that's close to 4 but coming from the left. So I'm going to say 3.9. And when I plug a 3.9 into this, right, 3.9, I'm going to have a positive answer in the numerator, and I'm going to have a negative answer in the denominator, and that's going to give me negative infinity. So the limit as x approaches 4 from the left of f of x equals negative infinity, all right? So since the limit as x approaches 4 from the left of f of x is negative infinity, we can say that x equals 4 is a vertical asymptote for f of x. That's it. Okay, so you had to justify. Okay, this up here was worth 2 points. This right here was worth 2 points. The next piece was worth 2 points also. So does f of x have any horizontal asymptotes? So for horizontal asymptotes, we have to check the limit of f of x as x approaches infinity. Okay, and if this equals a number, then we have a horizontal asymptote. So let's figure out what this limit is. So we're going to use our rules for f of x approaching infinity, and we're going to take our function, since it's rational, and we're going to divide every term by the power of x, the largest power of x in the denominator, which is x squared. So I'm going to have 2x squared over x squared plus 7x over x squared plus 3 over x squared over x squared over x squared. Okay, that simplifies. I'm still using my limit notation. A lot of you did this, but you didn't use any notation for limits, and it says justify your answer using limits. So that leaves me with 2 plus 7 over x plus 3 over x squared, 1 minus 1 over x minus 12 over x squared. And now we can do our direct substitution. If I plugged in infinity for all these x's, I would be left with 2 plus 0 over 1 minus 0 equals 2. All right, so I've shown that the limit as x approaches infinity of f of x equals a real number. So I can say since the limit as x approaches infinity of f of x equals 2, we can say that y equals 2 is a horizontal asymptote for f of x. Okay, full credit, all right, using limits. So as long as you showed me a limit, that the limit as x approaches infinity of this function equals 2, and then you said y equals 2 is a horizontal asymptote because the limit approaches, the function approaches a real number, then you've got it. You're good to go. All right, let's look at part D. This one asks us to find the limit as x approaches infinity of this function, and then to use that result to explain whether this has a horizontal asymptote or not. All right, this one's a little tricky. Our largest power in the denominator is actually square root of x squared, which, since we're heading towards positive infinity, is equivalent to x. So we're going to actually divide all of our terms by square root of x squared. In the denominator, we just keep it under the square root, so it's still square root of x squared. In the numerator, just to save myself some time, dividing by square root of x squared is the same as dividing by x. So I'm going to do that here. I'm going to keep going and simplify, making sure I'm using my limit notation. A lot of you did not use your limit notation at all, and you just started dividing and you weren't talking about it as a limit, so you lost some credit for that. In the numerator, that leaves me with 3x plus 2. In the denominator, it leaves me with square root of 1 minus 2 over x. Now I'm going to do my direct substitution, and as I plug in infinity, or a really, really large value for x, this is still going to be 3 times infinity plus 2, and this is going to be 1 minus 0. The issue is that this ends up still being infinity. Okay, so my limit of my function of 3x squared plus 2x over square root of x squared minus 2x equals infinity. Great. So do I have a horizontal asymptote? I would say there is no horizontal asymptote. Because for there to be one, that limit of infinity has to be a real number, because the limit as x approaches infinity of the function, I should name it so I don't have to keep writing it over and over and over again. It's not a real number, and that's plenty. So as long as you said something in accordance to that it continues to increase as it goes out towards infinity, or it does not approach a real number, so there's no horizontal asymptote. Again, it's using that definition of what we can use for justification for a horizontal asymptote. Okay, I hope this makes sense to you and that it helps you prepare for what question you may have tomorrow. Thanks.